So in this video we're going to be talking about open balls in a metric space. Remember, this is a metric space, the combination of a set and a metric defined on that set, the pair x the set and d the metric. And this definition in orange was the idea of an open ball, that we can take all the points around a certain point C which are r less than r distance away from C. And so now we're going to go over this definition. This is the idea of a general open set. So as you'll see, all open balls are open sets, but there's more open sets than just the open balls, which we've already talked about. So we're just going to get our 2D plane example, which is really easy to follow. So we take this, and let's say, for example, so this is an open set, but I'll explain why it's an open set in a second. So if we have say some funny shape in our plane, looks kind of like a kidney, I guess. So call this subset U, and this doesn't include the boundary. This dotted line means it doesn't include the boundary. It's just all the points within this shape, but not including the boundary. And we say that this is an open set if given any point x in U. So let's just pick any point. If any point has some open ball around it, doesn't matter the size, it can be as small as you like, has some open ball around it which is contained in the set. And so you can see that this has an open ball of some radius around it. Don't know the radius, don't really care either, but it has a ball of some radius, open ball of some radius around the points. And no matter how close you get to the boundary, there's always going to be some small ball of some radius around the point which is contained within the set. And really, the best way to exemplify a lot of these definitions in analysis is to look at the cases in which they fail. So let's take another plane, and let's make now our set including the boundary. So this is let's make another kidney, but this time include the boundary. So let's call this V. And what happens if we take a point that lies on the boundary? So say this point here that lies on the boundary. Well, you can see that there's no open ball of radius r around this point which is contained in the set, because r has to be greater than 0. This is one of our conditions of our open set. And so any ball of radius r you make around this point is going to contain, so let's say this is a ball. Remember, this can be really tiny, but it's always going to contain something outside the set here. No matter how small you make it, it's always going to contain something that's outside of the set, because this point lies on the boundary and you can't have an open ball of 0 radius. So this is not open. And so let's just take a look at a more obscure example. If we take the discrete metric on a set, so any set. Just a quick reminder that this doesn't have to just be points. It's just when we're looking at the discrete metric, it's easier to visualize if we just use points. So what are the open sets in the discrete metric? Well, let's just take some arbitrary subset of this space. So let's say these 5 points, for example. So this is U. So our requirement that this is an open set is if every point in this set has an open ball of some non-zero radius around it contained within the set. Well, remember from last time, every isolated point, so every set of the form just a single point, where this is some single point, is itself an open ball of radius some radius less than 1. This is the open ball of radius r around x for when r is less than or equal to 1. This is an open ball, just this point. So for any point, this is an open ball, this is an open ball, this, and this are open balls, and so our condition is satisfied. So what does this mean? Well, any set, any subset of a space with the discrete metric is an open set. And this is a really important idea, that a ball with that only contains one point can still have a pretty significant radius. And so you'll probably come across a lot of spaces and metrics which have really quite peculiar open sets, but all that you need is that every point in the set has a ball of some radius around it contained within the set, and then it is an open set. So in the next video we'll do some stuff on continuity involving open sets.